Li-Heng Chen is a software engineer in the video algorithms team at Netflix, contributing to the video encoding pipeline. He completes his PhD in 2022 at the University of Texas in Austin for the Laboratory of Image and Video Engineering, L. Balvik's group. His research background encompasses perceptual image and video quality assessment, image and video compression, and machine learning. Let's welcome Li-Heng.
Give us another minute. We're trying to readjust the settings here.
Maybe I can start now, like just using the trick that Ramsey mentioned, like pre-do something before it started. So I'm gonna. Oh, okay. So I'm gonna talk about like our AV1 film grain synthesis deployment at Netflix and what's next. So and my name is Li-Heng Chen. I'm working with Netflix. So this year, we successfully deploy the film grain synthesis at scale, so you guys can watch it on Netflix now if your device can support AV1 film grain synthesis without any issue. And yeah,
Good shows.
I will introduce the shows later, but as far as I remember, there's a Japanese drama called The Hot Spot. I personally really like it, and it has a lot of film grain on it. The Hot Spot. Yeah. Oh, I heard my song. Yeah, and Department Q, the one that Z likes, also has a film grain synthesis on. And Bahubali, it's an Indian movie. You never seen it? Yeah, you should watch it.
See here, but it doesn't go to the screen. It was working before, so. Okay, fine.
Okay, yay. Yay, so I already finished this slide. And yeah, so first I want to use some examples or analogy to demonstrate why film grain is so hard to compress. And it actually presented in many of our titles because some film creators them some nostalgia stuff. And it's hard to compress because the noise are random. So for example, if you subtract two consecutive frames with noise, you will see that the noise are presented at different locations. So if you subtract them, the variance will be like 2 times as large as just looking at a single frame, because if you have 2 random variables and they are independent, the variance of x1 minus x2 is like 2 times of the variance. And I'm gonna use one visual example to show how hard it is to compress it. So on the top, it's a source frame of a title called They Clone Tyrant. It's on Netflix. And the bottom one is a 4K encode at about 5 megs. But you can see that you can see some compression artifact, and it's because we quantize transform those noises. And if you cannot see it clearly, I'm zooming it in, and you can see they are quite disgusting. Like you can see some DCT patterns and ringings, whatever you call it. Yeah. Oh, I prepared this one. It's more disgusting. You can see here, yeah, you can see some chroma artifact and a DCT pattern, right? It's very, yeah. And but AV1 has a coding tool called film grain synthesis. It's designed for solving this problem. So I'm gonna introduce it. So for a regular like encoding scenario, we have an encoder, and then when you input the video, it will produce the bit stream, right? And then you send the bit stream to the device, and the device has a decoder, which is normative, like all the decoders should be able to decode all the conformance bit stream that is conform to the spec, and then you decode it as a video. And with film grain synthesis, you have more blocks. So the core idea is to denoise the video before encoding it. So if you remove the noise, you can imagine it will be easier to encode without those with less artifact. And if you subtract the denoised video and the source video, you will get a residual, which is basically the noise, right? And you are able to estimate some film grain parameter from the residual, and then you send the parameter as part of the bit stream to the decode side, and then you can use those noise parameter to synthesize the grain. And then when you play back, you just add it back, and then you will see the film grains being rendered. And in case you are wondering who invented this coding tool, like I referenced the paper here, and the inventor will present after me. Yeah. So basically, film grain synthesis model it models two things for the noise. So the first one is the pattern. It uses the autoregressive model to model the pattern. So basically, some noise are finer, and other noise could be coarser if the movie is older, right? And also another important aspect is the intensity. So noise could be stronger or weaker at different locations. So there's a piecewise linear function to model this, and I will introduce it in the next few slides. So basically, autoregressive model is used to predict stock market long time ago in a 1D manner, but most people got bankrupt by using this. But I would say the 2D version is pretty good for modeling the noise. So basically, it's a model that you can predict the next pixel by the neighboring pixel that is already reconstructed given an AR kernel. So I'm using a simple example. So if you want to predict this pixel, basically you have a previously reconstructed pixel with A0 to A3, which are the AR coefficients, right? And it's just a linear combination of them plus a white Gaussian noise. And if you keep doing this process, you're able to render a 64 by 64 noise template. So basically this template will look like a noise, and we use it to do film grain synthesis. And also the other aspect, as I mentioned, is the grain intensity. So it's modeled by a scaling function. So it's a function of pixel value. So for using this example, you can see on the hair, it's black, but you cannot see much noise, right? So the linear piecewise linear function will be of a lower value at a lower y value at a lower x value. But if you look at the background, which is gray, the noise is pretty strong, so it will go up as the pixel value goes up, like this. And I also mentioned about the decoding process, given the two models that is being used. So given the AR coefficient that's being estimated in the encoder and the there's a random seed as well, which I will talk about later. You are able to render a 64 by 64 template. And you also have a scaling function, which is also part of the parameters, right? And basically, how we do is you randomly extract a 32 by 32 patch, and then adjust the intensity, and then render it on the frame. And you can keep doing this with some overlap, and you can, basically, this is how the decoding process works. And you will notice that there's an offset X and offset Y. They are random value given the seed. So you can see that when you are rendering, it randomly extract the patches. So you can think about a question. So what would happen if the offset X and offset Y are not random enough? Like what's the consequence of that? And also, another question is, would it be better if we use a smaller block size, which is basically the green part? Like, think about it, because this will, like, we will touch on this for the AV2. And this is basically the result. So by rolling this out, we are able to reduce the 30% of the footprint with this tool on. And typically, it gives us a better visual quality. Oh, by the way, I want to mention that the higher the resolution or bitrate it is, the bigger gain we can get. So this is a tool that helps more on the high resolution part. And this is one visual example. So on the top is the source. On the bottom is AV1 without film grain synthesis. The bitrate is very high for that chunk. And if you enable AV1 with FGS, you can see that the bitrate reduced by almost threefold. And I think the quality is better, unless someone disagree with me here. Yeah, and it also has a side benefit. So because we render a noise on it, right? So the noise that we render kind of hidden the compression artifacts. So it's a visual masking effect. So on the left, I show the source, and then I show the regular AV1 that basically we encode the noisy content with AV1, so you can see a lot of compression artifact. And then the third one is like we denoise first, and then we do AV1 encoding, and there's no film grain synthesis. So you can see if we do the denoising, the compression artifact is lesser than the regular AV1 already. But like people may argue, hey, you remove the noise, you are cheating, right? So when we render back the FGS, you can see that the noise is not exactly the same as the source, but it's quite similar, and also it can hidden the compression artifact. And I'm also gonna share some tricks that we had when we are working on this. So the first one is to find a good denoiser, because I forgot to mention that the denoiser part is not a conformance, so you can use any denoiser you like. You can use a simple like 2D convolution with 1111, yeah, or you can use a very complex CNN filter. But the better the denoiser it is, the more successful, more likely you are going to be successful. And I'm going to use an anti-example. So I use FFmpeg denoising filter, and I use a very strong denoise setting. Basically, it means that it will remove too much. It will also remove the edges, right? So you can see that the residual on the third column that I display, it also has, it not only has a noise, it also has the edges, which is not what we want. So if you estimate the grain parameter with this residual map, you can imagine it will fail, right? Because the edges is also included, and your estimation algorithm may misrecognize that as part of the noise. So the noise that you render may be too stronger than the source. Or it could be even worse, like it could look something random that you don't want. Yeah, so that's the first trick. And the second trick is, as I mentioned, there's a film grain seed in the frame header, which is being used to determine make it random, right? And we realized that the film grain seed is actually quite important. So there are some seeds that are constantly good because they can generate a good template. And when you render it, there's no issue. But there's also some seeds that are very bad. So no matter what AR coefficient it is, if you use that seed, it will generate something that is too strong. And when you render on it, you will see some caterpillar-like pattern on it. So you want to avoid those seeds. So, and if you wonder what those seed is, we wrote a tech blog. You can search like with some keyword like Netflix, tech blog, film grain synthesis, and I put the film grain seed in that tech blog on the front cover. The font size is very small. I bet no one recognized that. And the third one is on a adaptive streaming scenario. So basically, when we are doing denoising and noise estimation, like because our content is very diverse, so you cannot be successful for all of the chunks, right? But you need to know when the algorithm is not doing good. So when you encounter that, you have to turn off the FGS for that specific chunk. And but this will cause inconsistency in quality within that scene, right? So what we further did is to disable FGS for all the chunks within that scene. This way, the quality is more consistent. You can imagine if you, within a scene, if you switch between green blocks and red box, it will look weird because there's an FGS off, which has the compression artifact, and then you turn on FGS, it becomes, it's a fake grain, so it looks very weird. And in an adaptive streaming scenario where we need to switch between different resolutions, we also needed to turn off FGS for the other resolutions because we may do resolution switching during playback according to the network conditions. So it's for the same reason we want to keep the quality consistent. And yeah, so it's been a long journey since AV1 is specified. And finally, we roll out at the full scale this year. And as I mentioned, there are some titles that has FGS ready, and if you can try watching it. For example, Chrome should be able to support it. Shout out to Google and Safari as well, and some newer iPhone. And I want to mention that this is our first Gen AR content on Netflix, not Gen AI, Gen AR. Hopefully you guys can get a joke. Gen AR. Yeah, and I think despite we successfully roll it out, I think there are a lot of work that video folks can do, no matter you are in academia or industry. For example, we don't have a good quality model now for film grain synthesis, because you can imagine it's pretty hard to measure the quality, right? The noise are located at different places, so you are not able to do pixel-wise comparison. So then how are you gonna measure the video quality? So this is one very important aspect because it can help monitoring the quality and also help tuning the recipe. And there's a new spec which is called AFGS1. You can, if you want to read it, you can search AFGS1 space Andre. And it allows you to signal film grain parameter that I mentioned in SEI message. So basically that means that you have the potential to stream FGS on other codecs like older codecs H.264 or HEVC. And there are also some improvements in FGS tool in AV1. So for example, like I think we did an improvement in the randomness, like the offset X and offset Y for the green boxes that I showed. So if we make it more random, like it will have less repetitive patterns. And also another way to address the repetitive pattern issue is to allow for a smaller block size, also the green box. So if your green box is smaller, you are more likely to sample different noise, right? And also there are some improvements in reference, which I'm not familiar with. If you are interested, you can ask Andre. Yeah, that's it. I'm on time, right?
We have time for 1 or 2 questions from the audience.
Okay.
Marcus?
Thanks. There's a recent comeback of the compact cameras with the different film emulsions graininess, so that you can actually get the shot as if you would be recording on analog film. Is there connection to the modeling of the grain here?
You mean the analog, like
Yes.
the film grain? I think it's different.
Yeah, but they try to imitate it now. You can buy cameras now. I think Fuji has some where you can choose which kind of film you want to use.
I agree. There may be a connection between them. So this is also one interesting aspect to research. And maybe there's a mapping, so they can map to the. So we don't need to estimate the noise. Maybe, right? There's a map. Yeah. So I agree. This is a good direction in the future.
So the you mentioned the denoise part, and the denoise part is a critical because it destroys noise. Destroys important signal.
Yeah.
How do you manage that you're not? How do you manage not destroying the useful signal?
So we find a complex denoiser, which I cannot tell you which one it is, and also there's a trick. So you can denoise. You can use a lighter denoise setting, right? So you don't need to remove all the noises. You just remove a thin layer of it, making sure that you don't break the edges. And it still looks pretty good. So this is one trick that we use.
Are you sharing
Thanks.
too much?
No, that one is fine, right? That one is fine. That one is fine. Okay.
More questions? Okay, maybe one more.
It seems to me that you are, but maybe I cannot get the full details, you are mostly addressing some kind of spatial noise. And I don't see too much temporal aspect. I'm under this.
You mean the denoising part or the?
Whatever, denoising or even with the noise itself. It has some kind
The generation, I would say, mostly.
Some kind
Yeah.
of spatial noise, but also you have some temporal aspect and spectral aspect. From the spectral one, when I say spectral, it's more the color and stuff like that. So I think you are touching that with the spatial noise, but the temporal relationship. How do you maintain a good temporal consistency with respect to the original content? So
I don't think the model covers that. The AR model doesn't cover the temporal aspect,
but
right?
we should somehow.
Yes.
We want to fulfill everything, right?
Totally agree with you.
Yeah.
Totally agree.
Andre, do you wanna
Totally agree with you. Yeah, you can.
I think it's true that the model doesn't cover the temporal aspect, but in fact, temporally the noise is decorrelated, right? So the original film grain noise, it's like each frame is separate. So actually what you want to achieve is you want to make sure that the noise is not correlated between the subsequent frame, because if it is, you would notice it. But I think it's kind of the model achieves it. You should try to make sure that the noise is not correlated, and that's.
It's really a frame-based
Yeah.
approach.
Let's thank the speaker again.